Hello. Uh, can you see my computer screen? Is it
Yes,
visible?
sir. Yes, sir.
Okay. In today's lecture, we will discuss about artificial neural networks. So I hope many of you already know about that is the artificial neural networks. So artificial neural networks is usually called um, a biological neural network inspired computational learning model. So here is the biological neural network. Uh, so in our brain, maybe we can say we have several units. Specifically, we call those the neurons. So neurons are connected one another, and they also communicate and share their words, and therefore they in our brain we have the biological neural network, that is biological network of neurons. So the artificial neural network, it is inspired from the connections and the units of our biological neural networks. Uh, so the neural network model, what's the purpose of this? The purpose of this is the actually the computation. Okay, the computation. How a human learns, how human computes something, how human memorize, how a human store the knowledges. So all these things specifically based on our biological neural networks. And that's why that is neural network scientists, they also try to kind of mimic the same thing. Okay, mimic the same thing. So in our biological neural network, it consists of several processing elements. Usually we call those are neurons. Before processing, it will also take several inputs. Okay, we have some input organs and also output organs. Okay, from the eye we can maybe perceive the environment, or we can say we can see something. Then after seeing that, the brain process, and after that the brain that is produce the output, like whether this one is cat, if this one is dog, or this one is an image of flower or something. Okay, so that means we have so as we are discussing here, that is the artificial neural network. So let's say uh, in our if we want to design artificial neural networks, then at first what we need to think about, at first we need to think about, uh, that is the problem. What's the problem? That is what's the problem we want to solve. Like here is an example, that is we want to maybe predict someone's CGPA, or we can say the score in exam, based on two things, like the hours of sleep and hours of study. Maybe we have a data set for that, data set of maybe of uh, maybe we can say uh, like maybe we can say that is 1 lakh students data, uh, Brack University and other universities. And we have just this data, that is their sleeping hours and study hours, that is average sleeping hours and average study hours, and their CGPA. It is given in a data set. Okay, it is given in a data set. And now, so we want to design a neural networks for that. Then what we have to think about, at first we need to think about like how many features are there. So how many features? Here we can see two features. One is hours of sleep and another one is hours of study. So we have to think about how many features. And based on that, we have to actually select the number of neurons in our input layer. So this is called the input layer. So input layer, that means in our input, we have hours of sleep and hours of study. So we have to design the input layer. So input layer. So this is the input layer. In this input layer, we have just two neurons. Why two neurons? Because we have two features. And then next thing is we have to think about the that is the output layer. That is the output layer. What will be our predicted score? The predicted score it will be some continuous value like maybe 3.99, 3.87, 4.0, maybe 3.56 like this way. Okay, so that means in our output unit we will get what? We will get some continuous values. So this is a kind of regression problem. Okay, regression problem. So if it is a regression problem, that means it will produce just one value. So here, if it is produced just one value, then we can say in our output layer, this is output layer. This is called the output layer. Output layer. So in our output layer, we have to place just one neuron. So here is just one neuron. Okay, one neuron. So that means based on the number of features, we have to decide the number of neurons in input layer, and uh, based on our that is the output number of outputs, uh, we have to select the that is number of output units or output neurons, and then we have to form the we call this the hidden layers. Okay, we have to design the hidden layers. So the number of hidden layers and the units of neurons in each and every hidden layer, this is actually user defined. So user defined and problem specific. So sometimes you can consider like that is one hidden layer. So in this case, we can see that we have one, two, three, four hidden layers. Okay, four hidden layers. In our first hidden layer, we have one, two, three, four neurons. In our second hidden layer, we have one, two, three, four, five neurons. And in our third hidden layer, we have one, two, three, four neurons. And in our fourth hidden layer, we have one, two, three neurons. Okay, three neurons. So this part actually user defined and problem specific. Sometimes this is also we have to decide these things kind of the trial and error basis. Okay? Trial and error basis. So that means the hidden layer here in this case we can see in this case these hidden layers usually we call these are the black box. Okay, these are the black box. Why black box? I will tell you that. Uh, and also based on the number of hidden layers we decide whether this network is deep or this network is shallow. Usually in shallow neural networks we consider that we only have one hidden layer. Okay, one hidden layer. So if there is one hidden layer, then usually we call it shallow neural network. If more than one, then usually we call deep neural network. This is theoretically. Theoretically, two hidden layers means the deep, but actually in deep neural networks, usually we have 10, 25, 100 hidden layers. Okay, but theoretically, if just more than one, that will be your deep neural networks. Uh, Before the concept of deep neural networks, specifically if the number of layer is greater than one, hidden layer greater than one, we usually call those neural networks as multi-layer perceptrons. Okay, we studied these things in using the multi-layer perceptron, not specifically the deep neural network architecture, but maybe for last 10 years we mentioned that this is deep neural network architectures. Sorry. So here so that is the case, but why this part is called the mysterious, or you can say the black box? Specifically, this kind of neural networks, we can see that here is the hours of study and also there is hours of sleep. This is the input, and based on the maybe 1 lakh data, if we train this neural network, finally it will maybe perfectly, it can say that that is, if someone's study hours are 10 hours per day, and maybe the sleep hours is 6 hours or 7 hours per day, then what will be the predicted CGPA for that student? uh, okay, so it can do that. Okay, it can do that, sometimes very perfectly. Okay, but the problem is we cannot explain that why it is mentioning that there is maybe the CGPA of that student will be, the predicted CGPA will be 3.98. Why this one? So if we ask why, then it is difficult for this network to answer that question. That is why. Okay, that's why it is called mysterious. And in another way, we can say that, okay, this is the output, but if we do some reverse engineering, can we find something like this, some mathematical formulation, so that maybe it will answer the kind of a kind of generalizations, like like our different formulas. Okay, different formulas. Based on formulas, we will get the output. Okay, and here, that is, can we do some reverse engineering for that? There is, can, for this answer, maybe you can say, that is, can we find something, some generalized equation for that? Most of the cases we will not get that. Okay, so that's why, we call it's a black box, because we cannot do some form of reverse engineering on that case. There is no straightforward equation for that. Okay, so there is no equation. uh, okay, so that is the black box. So here what we have learned, that is, if we want to design a neural network, at first we need to think about, that is, how many features in our data set we have, and based on that we have to select the number of input layer, in neurons, and then what will be the output. Based on that we have to select the number of output neurons, and then the hidden layer neurons, the number of hidden layers, and there is units of each and or neurons in each and every layers. How many neurons we need to put, that one is problem specific and user defined. And also the shallow and deep networks, if the hidden layer is just one, then usually we call it shallow neural network. And if the number of layers are multiple, there is more than one, usually we call it deep neural networks. And what else we have learned, that is the definition of neural networks. And also there is the, we learned that the hidden layer neurons, those are kind of the black box. Okay, now, as it is mentioned that there is, the artificial neural network actually a kind of emulator of our human brain. So we can see that in human brain there are several areas of human brain, and our brain is very much powerful, and different part of the brain actually works differently. Like, so this part we can see, this part is called the motor area. So to control the voluntary muscles, okay, muscles. And then this part is called the sensory zone, okay, sensory zone or sensory area. So for the temperature, pain, pressure sensations. And here is the frontal lobe, okay, frontal lobe. So it controls the movement, problem solving, concentrating, thinking, behavior, personality, mood. So lots of actually functionalities of this. Okay, so like this way, different parts of brains actually responsible for different functionalities. um, but we have the neural networks. Actually we want to simulate the brain, but the problem of our traditional neural network is this, that is, we can see that the human brain we can segregate different parts. Okay, human brains can be segregated like the motor area, sensory area, frontal lobe, there is temporal lobe, and occipital lobe. So different segments, and one brain actually works for different purposes. Okay, so it can memorize something, it can that is uh, successfully detect the objects, successfully detect the faces, uh, and also there is it can test different things. Okay, so it can solve different problems. And also it can speak using different languages. So different languages. It means that is the same brain, but different functionalities we have. But usually, in case of neural network, one neural network is for one purpose. Like maybe if we design a neural network for object detection, and then it will do only the object detection. Okay, so that's another problem. Um, so this kind of that's why this kind of AI usually we call the generalized AI, or we can say the problem specific AI. Okay, uh, uh, then actually we want to develop something like usually we call artificial general intelligence. Okay, AGI. So that means like the human brain, the the same brain performs different functionalities. In AGI, we want to develop something that is the same neural network, but it will maybe uh, it will learn the languages uh, like any chatbot, and it will also detect like the different objects. Okay, uh, so it can sense different things. It can speak. Okay, so that means same neural network, but uh, the different purpose it will used for different purposes. So one of the limitation of our traditional neural network is it is just only one neural network is designed for one purpose. Okay, and as we already have seen that actually it is depend on the input, that is the input feature, how many features in this problem, and based on that you need design the neural network. But for other cases, uh, you can see here for human brains cases, the inputs are dynamic. Okay, sometimes maybe the feature can be one, sometimes feature can be thousands, but it still need to process that. Okay, now we need to find out that is what's the difference and what's the similarity between our biological neural network and our artificial neural network. Okay, so in biological neural network, specifically we can say that we have a cell uh, and, we can say that there is a neuron. So in that neuron, we have the nucleus. Okay, so a nucleus and the cell body you can see here, and axion and dendroids and synapses, and here the dendrites. Okay, dendrites. So specifically for this neuron, this is the core module nucleus. This is the core module for computation. Okay, computation. And then after computation, one neuron can communicate with another neuron, so they can connect it. So this is the age. Okay, usually called axion. And then we have the synapse. Okay, and synapse, that means to send something, some information, it will use the synapse. It will use the synapse. And to receive something, it will use the dendrites. Okay, this is the concept of biological neuron. Here we can see that there is one neuron and another neuron is connected. So this is one neuron and this is another neuron. So here the synapse and the dendrites. Okay, and the dendrites are just uh, sending and receiving informations from one neuron to another neuron. But we have actually many neurons. We can say that is the billions of neurons in our human brain, and so billions of neurons means it's huge. Okay, it's huge, and that's why the computation capability of our brain is also huge. Okay, So if we can see that one neural network consists of billions of neurons, I think in our traditional machine, uh, we cannot hold that much neurons. Uh, so there are several purposes we can use the neural networks. That is, we can say speech recognition, facial identification, reading emotions, recognizing images, analyzing sentiments, and for driving the autonomous vehicles, disease diagnosis. So many applications we have. Many applications we have. Now we can see that is our uh, that artificial neural networks and also the biological neural networks. What are the similarities here? Okay? What are the similarities? We need to identify the similarities. Okay, then we can see in our biological neural network, some of the units actually those are input units. So it will perceive the environment. Like we can say here is our eye, and it perceives the this cat. So in our computer neural networks, so we have also the input units. Okay, these are the input units. So that means, like our biological neural networks, we have also the input units. And like our there is the biological neural networks, we have some we have some output units like our mouth or something. Uh, so we can say that this is a cat. Okay. So here is also the same thing in our artificial neural networks. We have also the output unit. So that means input unit, then the output unit, input layer and output layer, and then the neurons are connected to each other in our human brain. One neuron is connected to another. And here is our hidden neural network. In hidden layers, the input the neurons are connected. Okay, the one neurons, every neurons are connected to each other from one layer to another layer. So this layer neurons will connect to this layer neurons. If we consider the fully connected neural networks. And another thing is for each and every neurons, this is called the computing unit. Okay, so this neuron is our computing unit. Uh, so we don't know actually what are the computations inside any neuron. Okay, but we human are very limited in computation because we know the major there is four major computations like the addition, and then subtraction, and then multiplication, and then division. Okay, so those are the cases here, and that's why we also do something multiplication, and then summation of those, and then maybe using some nonlinear function, we need to transform those numbers to a nonlinear number. Okay, so those are usually in our artificial neural networks, but we don't know actually the computations of our biological neural networks. This is unknown. This is only Allah knows or God knows. Okay. And another thing here is in our artificial neural networks, usually we do two kind of processing. One is called forward processing, and another one is backward processing. The backward processing is for the learning purpose. Okay, the learning purpose, or we can say learning in neural networks. But we don't know that is whether actually the biological neural network works in like the backward propagation or not. Most of the cases, the uh, the neuroscientists mention that actually there is no back propagation or backward propagation in our brain. Okay, but in our neural networks we have that. There is the forward propagation and backward propagation. Uh, so now, if we want to design a neural network for a classification problem, then what we have to do? So I have already mentioned one of the neural network design for the regression problem. Okay, regression problem. But if we want to do something neural network for the classification problem, then what we have to do? So again, at first we need to see that how many features in our data set. So we can see we have like this is the four features we have. Four features we have. So sepal length, sepal width, petal length, and petal width. Okay, and we have the species here like okay. So we have four features. Okay, this data set is the iris data set. So iris data set means iris is a flower. It has three species. Okay, three species. And based on the petal length, petal width, sepal length, and sepal width, we can differentiate those uh, flowers. Okay, those flowers. So that's the our data set is. So in this data set we have four features. Okay, so as I already mentioned that to design our neural network we have to use four neurons in our input layer. So here is also the same for the classification problem also. Okay, and now there is number of classes. How many species of that flower? So we know that three species. One is called Setosa, Virginica, and Varchica. So Setosa, Virginica, and Varchicolor. Okay, so these are the three species usually. So that means this is a three-class problem, multi-class problem, but the number of classes here three. So what we can do, we can maybe we can consider three neurons in our output layer. One is for Setosa, one is for versicolor, and one is for versinica. Okay, so output unit. If the classification problem is binary classification problem, binary means two class, then we can actually think about like two neurons, or we can think about also one neuron because we can see the one bit is enough for presenting like 0 and 1. Okay, so on that concept we can consider one neuron, or maybe we can consider two, one for 0 and another for 1. So that means for classification problem, uh, the number of features equivalent to the number of neurons in the input layer, and number of classes equivalent to the number of output neurons in output layer. And then hidden layer, this one is again problem specific and also the user defined. Okay, user can maybe consider 25 layers. User can consider like 2 layers, 1 layer, and each and every hidden layer there is the number of neurons. It will maybe that will also user defined. Okay, that will also user defined. Okay, now what we want to learn, we need to learn about that is the neural network training and testing. So for the training purpose, the neural network it has uh, two phases. One is called the forward propagation, another one is called the backward propagation. Forward and backward propagation. So we will discuss now that is what is forward propagation and how to find out the predict and the predicted numbers. Okay, in forward propagation. And backward propagation, that is how to update the weights for training the neural networks. Okay, so we will discuss about that. Okay, at first the forward propagation. Okay, forward propagation, specifically the forward propagation is to find out uh, the predicted values. Okay, predicted values. So in forward propagation, what we have to do, let's say we have a neural network for this data set, and in this data set we have two features like f1 and f2 and the output. Okay, so that means if input is 0 and 0, then output is 0. If input is 0 and 1, then output is 1. If input is 1 and 0, then output is 1, and if input is 1 and 1, then output is 0. Okay, so uh, so for this neural network. Okay, so So we want to design neural network for this data set. And at first we can say how many features. We have two features, so that means two input units we have. And here is the this classification problem, 0 and 1 classification. So we can add one neurons or maybe two neurons in our output layer. Here we have added one neurons, okay, one neurons. And we have designed our mm, hidden layer. In that hidden layer we have considered that we only have one hidden layer, that is a shallow neural network. And in that hidden layer we have just three hidden neurons, okay. So here is the three hidden neurons. Now we have to form the neural network at first. That means for the input layer neurons, it should be connected to the hidden layer neurons, and hidden layer neurons should connect it to the input layer neurons. Now we can see that here is the input layer neuron. It is connected to the hidden layer neuron. This is the connection. And input one, and that is first input. That is, we can see this is, if we consider the x1, this is the x1. X1 is connected to the h2. X1 is also connected to the h3. That is hidden unit 3. Similarly, for the x2, x2 the another neuron. The x2 is also connected to the hidden 1. X2 is also connected to the hidden 2. And x2 also connected to the hidden 3. Okay, hidden 3. So that means the full connections here. And hidden layer units are also connected to the output layer unit. So here is the connections, okay. So that is hidden 1 connected to output unit, hidden 2 connected to output unit, and hidden 3 also connected to output units. Now, so these connections, each and every connections, we have to assign the weights, okay. So like this is the W1, the connection between X1 to H1. And connection between X1 to H2 is the weight is W2. And connection between x1 to h3 is our w3, and x2 to h1 is w4, and x2 to h2 is w5, and x2 to h3 is w6. That means we have to assign weights to each and every connections, okay, each and every connections. So now the network is formed, okay, network is formed, and we want to perform the forward propagation, okay. So before considering that, what we have to do, uh, this is a simplistic form of neural network. We have some more, actually something more. We will discuss this one later. Uh, so in this simplistic form, we can see that for each and every weight, so each and every weight, we have to assign some random values. Maybe within 0 to 1, okay, within 0 to 1, those are random values. Usually we call those are the weights. So for W1, maybe we need to assign something. For W2, we need to assign something. W3, we need to assign. So for the initialization, we have to assign those words. Assign those words. Okay, assign those words. And now, for a forward propagation, what we have to do for each and every hidden unit, like this is the hidden unit of hidden layer 1, H1. We can see that in H1, the inputs, these are the two inputs. Okay, these are the two connections. And one connection from x1, that is from input layer 1, that is x1, and another connection from x2. And weight, we can see that there is this weight is w1, and this weight is w4. So in h1, what we have to do, we have to compute some linear just relationship. Okay, linear relationship. We can see the input is x1, and the connection weight is w1. So here is x1 w1. You can see in h1, the h1 will form a linear equation. That is x1, input is x1, and the weight is w1. And in another connection we have the input is x2 and weight is w4. So here is the x2 and w4. So the h1 in hidden unit 1, we will get x1 w1 and x2 w4. And for H2, that is hidden unit 2, we will get X1 with W2. This is the W2. X1 with W2 and X2 with W5. So form the linear equation for that. There is x1 w2 and x2 w5. Similarly, for H3, here is x1 and w3 and x2 w6. So x1 w3, x2 w6. So this is our hidden tree. Okay, so that means we will get what? We will get the value of h1, h2, and h3. Now we can see that those are just h1, h2, and h3. Those are just linear. Uh, those values we got from the linear equations. Okay, just linear combination of inputs and their weights. Uh, but most of the problems in this world actually usually called the non-linear problem. Okay? So just only if we want to classify something, or if we want to maybe predict something using some regression method, the linear line, or we can suggest a linear line, will not be enough for all the cases. Okay? So we need some form of non-linearity on that case. So to make this value nonlinear, what we have to do then, we will pass this value to using any activation function. So activation function usually we call them uh, nonlinear function, and also like there are several activation functions we have, like the sigmoid activation, radio activation, tanh activation. Okay. Okay, so that means these values we have to pass through some form of activation function. Let's say we will pass it the popular sigmoid activation function. So that means we can say the sigmoid value, sigmoid of h1 will provide us the non-linear values. The sigmoid of h2, sigmoid of h2. So here is the sigmoid of h1, then this is the sigmoid of h2, and then sigmoid of h3. Okay. So that means the linear values like h1, h2, and h3, what we got from the linear combination of input and weights, then we have to pass through the nonlinear equation using the sigmoid. So here in hidden units, we will get the now the nonlinear values, like we can say sigmoid of h1, sigmoid of h2, and sigmoid of h3. So these sigmoid of h1 and h2 and h3, now we have to find out the values of output. So usually we call the output sum. Okay, so output sum. Output sum. So output sum. Okay, so it will be the combination of, again, the linear combination of the sigmoid of h1, the sigmoid values, and the weights. So sigmoid values and the weights means here is the sigmoid of h1 times w7. So that means sigmoid of h1 times w7, and then plus of sigmoid of h2, can say this value, sigmoid of h2 times the w8 plus of the sigmoid of h3 times w9. Okay, w9. So here output sum sigmoid, these are the sigmoid values. Okay, sigmoid values. So we will get the output sum on that case, output sum, and then what we have to do, output sum. So now we got the output sum. Okay, And here we can see that those again we got from the linear combination of those values. Okay, linear and this linear combination, linear relationship. So this output sum, now what we have to do, we have to pass to again to some activation function like the sigmoid of the output sum. Sigmoid of the output sum. We want to pass this one to find out the predicted results. Okay, the predicted prediction, the predicted results. Okay, so that means this will be our the predicted values. Predicted values. That means after passing through the sigmoid function, the output sum, we have to pass through uh, the sigmoid function to get the predicted result. So this is actually goal of our forward propagation. Goal of our forward propagation. Now, um, let's say we want to find out the predicted value using our some maybe random values. So let's say these are the random values. Okay, that means we have assigned the W1 equal 08, W2 equal 04, and then W3 equal 03, and this is W4 equal 02, W5 equal 09, and W6 equal 05, and W7 equal that is our 03, W8 is 05, and W9 is 09. So this is just in our first step, or you can say in our first iteration, those values we will just assign randomly between 0 to 1. The random numbers we have to generate between 0 to 1. So these are the values. Let's say these are the values. These are the words. Actually, we call those are also learning parameters because uh, for our data set, the input we should not change the input, or there is no scope to change the input. But we can just update the weights, that is the W1, W2, W3 like this way. Okay. So that's why these are the learning parameters. That means in this network, we have just W1 to W6, the simplified form of this network because we didn't consider the bias here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the 9 learning parameters in our simplistic form of this network. So now, if we consider that we have input, we have input x1 and x2 here. We have input that is x1 equal 1 and x2 equal 1. So that means this is the input. Okay, this is the input for this one, for the instance number 4. X1 is 1 and x2 is 1. If we pass this one as input, okay, pass this one as input, then x1 and x2 we know that, and also we can see that that is our target, or we can say our expected value or original expectation is 0. So if we just if we just pass 1 and 1, the expected output here is 0. Okay, so we want to get the 0. So after completion of the training, actually we will find here the 0. Okay, that's the training. Initially we have to train so that our network can produce the values of whatever mentioned in your original data set. Okay, so if we pass this one for in our first iteration, if we pass these values, then in forward propagation, what will be the predicted value in forward propagation? At first, we need to find out the H1, H2, and H3. That means the H1 here, H1, then H2, H3. So hidden layer values, okay? Hidden layer values we need to find out. So we know that the equation of forward propagation, the H1, it is x1 times W1. So like this one, x1 times W1. plus of x2 times w4. So here this is the x2 and here the w4. Uh, so x1 is what? X1 is 1. Okay, in our case x1 is 1 and w1 is 0 0.8. 0 0.8. The plus of x2 is also 1 and w4 in this case it is 0 0.2. So now you can see here it is zero point 0.8 plus of here is the 0.2. So that means it is 1.0. 1.0. So that means H1 is 1.0. Similarly, we have to find out the values of H2, and in this case, H2 is X1. X1 is X1, and then W2 plus of X2 W5. And in this case, X1 is 1, and W2 is what? W2 in this case it is 0 0.4. 0 0.4 plus of, and X2 is 1 times 1 times W5 is 0 0.9. So in this case, it is like 9 and 4. Uh, so it is 1.3. Okay, 1.3. Similarly, we have to find out also H3. Okay, H3, the same. So we will get the H1, H2, and H3, and we can see that the H1, H2, and H3, you will get those values. Okay, those values you will get. So now we got the H1 equal 1, H the hidden layer values, that is H2 equal 1.3 and H3 equal 0 0.8. So these are the hidden layer values. Now, and next thing is we have to pass these values to a sigmoid function, sigmoid of 1. We have to calculate the sigmoid of 1. And then we have to calculate the sigmoid of 1.3 to make it nonlinear. And here it is also, that is sigmoid of 0 0.8. Okay. So now we can see that this is the case. There is sigmoid of 1.0. It is 0 0.731, and sigmoid 1.3 it is 0.785, and sigmoid of 8 is 0.689. So what is the sigmoid function? Okay, what is the sigmoid? So here is the sigmoid. This is called the sigmoid function. So it is the 1 by 1 plus e to the power minus of g. Okay, so that means we can see that this is a curve or nonlinear nature. We can see that maybe before these values, if we got some negative, very negative values, then it is nearly zero. Okay, nearly zero. And then if we got some very positive values like greater values 5 and 10, then we will get it is 1. Okay, and all other cases, these values it will be like uh, the the linear growth. Okay, linear growth.
Sir, I have
uh,
a question.
Hello.
I have a
Follow.
question.
Yes,
Sir,
please.
do we use sigmoid only for binary classifications?
No.
Because
Why?
how can we use it for more than one class? Like if you want more than two classes, if you have.
So here we can see that if you can see last layer of the neurons, last layer of the neurons. You can see here in this case, at this case. So in this case, we have like the values is we can say the values are you need, if you need the binary class, then at this stage you can apply maybe the sigmoid function. If we apply the sigmoid function, then the last layer, that means in the last layer, so it will maybe generate something, the probabilistic result. Okay, probabilistic result. Then the probabilistic result you will get from maybe 0 to within 1. So 0 to within 1. And if we have the like three class, like one is for Setosa, another is versicolor, another is versinica. Okay. So actually it will provide us the probabilistic result. And probabilistic result, you will get three values here. From the three values, you will get the probability of first one, you will get the probability of second one, and you will get the probability of third one.
Sir, how will we get three values? I'm confused here.
How we get three values? Okay, I will show you the example. Okay, because I have this example also. How you will get three values? Of course, we will get three values, but because three inputs we have. Okay, let's say we have the network. Where is my network? Yeah, this one. In this case, if we compute something like the values from hidden to output, here is hidden to output and hidden to output, you should get one value from here, and another value maybe you will get here, and another value maybe you will get here.
Okay, okay, sir. Now I get it.
Yeah, yeah. So we will get three values. Okay, and for each and every value you will get that is the probability for that. The probability of Setosa maybe you will get like 0.02, and for probability of versicolor maybe we get 0.01, and for virginica maybe we'll get 0.5. So then we can see that which one has the highest probability. This one, okay, 0.5. So that means we can classify this one as virginica. I think you got the point. So here is the sigmoid function. Okay, that means we can see that if we pass the one, that is the one, then what will be the value of the sigmoid? The sigmoid of one, it will be 1 by 1 plus e to the power minus 1. So if we do the math, then we will get the value. So e to the power minus 1. Okay, so you will get 0.73. Similarly, we have to find out the sigmoid of 1.3. That means on that case, it is 1 by 1 plus e to the power minus of 1.3. Okay. So then we will get again the value like it is 0.785. And then for maybe 0.8, you will get 0.6899. Okay, 6899. So it means here from here we actually we get the nonlinear values like 0.73. Then in this hidden unit we will get the 0.785, and in this unit we will get that is 0.689. Okay. Now we have to continue the forward propagation. Okay, forward propagation. Uh, so we got this the hidden layer values and also the sigmoid values. Sigmoid values. Okay, sigmoid values. Now what we have to do, we have to uh, actually find out the value of our output unit. Okay, value of our output unit. On that case, we have to apply the linear combination of our sigmoid of hidden layer values and also the weights. Okay, so here is this. We can see that is our 0.73 times 0.3. Here is the 0.73 times 0.3. Actually, the sigmoid of H1 times W7. And then sigmoid of H2 H2 times W8, that is 0.79 times 0.5. So here is the 0.79 times 0.5. and 0.69 times 0.9, 69 times 9, then we will get what? We will get this is 1.235. So this is what? This is called output sum. Okay, so O sum or output sum. So output sum, we got 1.235. So here is this. There is 1.235. Okay, we got that. Now the next thing is again we have to pass this value to a sigma function, or you can say an activation function. So here we can see that there is a sigma of 135. Again, there is the same equation we have to follow, like 1 by 1 plus e to the power minus of 1.235. So what we will get? We will get this value. It is 0.77469249. Okay. So this is our predicted results or calculated results. So this is the result. Okay, the predicted results. So now we can see there is what's the target? Our target, if we just input this one, then target is what? Target is 0. So we have input like x1 is 1 and x2 is 1, but our target it was just 0. But what we got? We got like 0.77 here, 0.77. Our target is 0, but our prediction is 0.77. So that means this is far from our target, far from our target. We have initialized those weights just only using these values, and that's why we can say that is the calculated value is 0.77. Now what we have to do? Actually, we have to change the weights. Okay, change the weights. So we can see that in forward propagation, whatever in our equations, we have the input values, and from the data set we can see that for this input we cannot change this input to get the 0. Okay, so the input is fixed. What we have to do, we can only update the words, only we can update the words. So that is we have the scope to update the words to get the 0 here, to get the 0 here. And that's why uh, we need some policy for updating the words. So how to update the words, that will be considered in our next part of our of this lecture. That is the usually we call backward propagation. Okay? Backward propagation. So in our backward propagation, what we have to do, at first we need to find out that is the error. We call the output sum margin error. Okay, output sum margin error. The error we have to compute, like the target is 0 and calculated it is 0.77. So usually the error we compute like original minus the prediction. Okay, so original minus the prediction. Here is also the same thing. Originally we want to get the 0, but our prediction is 0.77. So here you can see this is target minus calculated. The output some marginal error will be negative 0.77. Okay, so this is the error. Now this error, actually now we have to find out that is the policy to update the weights based on this error, based on this error, that is based on the error, based on the error. That is whether we need to increase these values, that is this weight like 0.3 to something, we need to increase or we need to decrease. Similarly, whether we need to increase the 0.5 or decrease the 0.5, whether need to increase the 0.9 or increase the 0.9. Okay, so using the back propagation, what we will do, we will think about this layer first. Okay, update of weights of this layer, and then update the weight of this layer. Okay, so we can see that it is kind of, that is the from end to the start. Okay, end layers to the start layers. So that's why it is called the back propagation, okay, or backward propagation. So that means the uh, how to change those values to change our outputs. Okay, to change our outputs, and considering that we have to change that. We have to change it. So now we can see at first that in our last layer what we have done in our last layer to compute our this value, that is the compute our result, compute our result, that is compute our result, compute our result. What we have done like we have used the sigmoid of the output sum. Okay, sigmoid of the output sum. So result we got from sigmoid of the output sum. If we can remember that, okay, if we can remember that, here is the output sum. To find out the result, we take the sigmoid of the output sum values. Okay, so we should start from here. We can see that that is the sigmoid of the output sum is result. Okay, sigmoid of the output sum is result. Now, if we take the derivative of this sum, that is rate of change of our sum, uh, it will change our results also. Okay, it will change our results also. So that's why if we take the derivative, so here is the derivative of the uh, sigmoid, and this is nothing but the d sum d result. Okay, d sum by d result. So now we can see here there is d sum by d result, that is the derivative uh, of our sum with respect to the result of this error. That means we can see here there is target results minus calculated results. So the target results is 0 and calculated is in that case it is 0.77, and we can call this one as the delta sum. Okay, that is rate of change of sum, rate of change of sum. Okay, so this equation we can use simply use here. One important thing here is we are taking the derivative of the sigmoid. Okay, we can see that this is the sigmoid s. So taking the derivative of the sigmoid function. So the derivative of the sigmoid function, it has uh, 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 an interesting property. Okay, interesting properties. And what's that? If this is the sigmoid function, actually this is the sigmoid function. Sigmoid of x is 1 by 1 plus e to the power minus of x. So if we take the derivative of this, that means if we try to find out the sigmoid of x, so it is nothing but like the sigmoid of x times the 1 minus sigmoid of x, 1 minus sigmoid of x. So if we take the derivative, that means the derivative, we can actually take the derivative with respect to e. Okay, so and after maybe we can say simplification, you will finally get that this is the case. Okay, this is the case. There are many actually the derivation of and proof of this. I didn't put that proof here. Uh, so in this case, we can see that derivative of the sigmoid of x. So it will be nothing but the derivative, the sigmoid of x and 1 minus sigmoid of x. So sigmoid of x and 1 minus sigmoid of x. So it is easy to compute because already we compute the sigmoid of x. Okay, already, so no need to recompute those things again, because sigmoid of x already we compute, and that value and 1 minus of again sigmoid of x, that value, if we multiply these two, then we will get the derivative of the sigmoid of x. So this is very interesting property because actually it will save the computation time. So sigmoid of x we have already computed, because we can see the sigmoid of sum we have already computed. Okay, already computed. So whatever we get from the sigmoid of the sum, that value times 1 minus of that value, that will be our derivative of the sigmoid of the sum. Okay, now uh, so here as we can see here in this case, the delta sum, it is there is derivative of the sigma of the sum times target result minus of calculated results. Okay, target results minus calculated results. Here is this. That is delta output sum. If we just write in simply, we can see it is uh, derivative of the sigma of the sum times the output sum margin error. Okay, output sum margin error. So the derivative of the sigma of the sum is what? Derivative of the sigma of the sum, it is uh, the sigma of the that is the sum is what? In our case, sum is 1.235. So that means this value 1.235. So 1.235 and the derivative of that. Okay, derivative of that, and output sum margin error we know we have calculated already, minus of 0.777. Okay, now for this one what we need to do, the sigma of the sum. Okay, derivative of the sigma sum, it is sigma of the sum, and we know that sigma of the sum is, previously we have computed that. So the sigma of the sum is what? 0.77, let's say 775, 0.775. Sigma of the sum, this one is 0.775. So to compute the derivative of the sigma of the sum, we can write this one as 0.775 times 1 minus 0.775. Okay, so this will give us the value, that is our derivative of sigma of the sum and times this is the output sum margin error. Okay, output sum margin error, then we will get this, that is our delta output sum. Okay, minus 0.134398 something. Okay, so we will get this. So this is our delta output sum. Okay, delta output sum, or you can say this is delta sum. The value of our delta sum or delta output sum, it is minus of 0.1343, like this. Okay, 1343, 1343. Okay, now what we have to do that, so we got this, so we have this. Okay, now we have this, but according to that or using that, we have to update these values. So how can we update them? How can we update those values? So if we can see actually, uh, in our that is forward propagation, how we got the output sum, the relationship between, that is to calculate the output sum, what we have done, the output sum, the hidden layer results, that means that these values we have to multiply with this one. Okay, so here is that is this is called these values usually we call the hidden layer results. Okay, hidden layer results after applying the sigmoid. So we got these values, so that is the hidden layer results, and then we multiply with our the weights of hidden to output layer. Okay, so weights of hidden, these are the hidden to output layer. So if we consider those are the vectors. Okay, so h result is vector and w h0 is vector. Actually we got what we got like the output sum. Okay, output sum, the hidden layer results, actually we have the h1, then h2 and h3. Okay, so h1, h2 and h3. So these are the hidden layer results, and then we have the w hidden to output. So w hidden to output is we assume that the w7 and then w8 and then w9. Okay, so w9. So here is this. Uh, so we have multiplied this. Okay, that means h1 times. Actually, not the h1. It is sigmoid of h1. Okay, sigmoid of h1. Sorry, the sigmoid of h2 and the sigmoid of h3. Then we can see that this is the case, that is sigmoid of h1 times w7 plus of sigmoid of H2 times W8 plus of sigmoid of H3 times W9. That is output sum, that is our sum, okay, or sum or output sum. Okay, that is our output sum. And that's the equation here, okay. That means we wrote those things in vector form. Now, if we take the derivative of this equation with respect to the output sum, okay, because we can see that the delta sum is there, so we can take the derivative of this equation with respect to output sum, then we will get do sum by here is the dwho, and then this is the hidden layer results, okay. Do sum, that means equation with respect to, that is the w, uh, then we will get, we can see this one, we are taking derivative with respect to w, so this will be on that case 1, and here is the do sum by dwho, okay, do sum by dwho. That means this one delta was sum by delta who, it is the hidden results. So in this case, we can see that actually what we need to know that is how much we need to change the the W, that is the WHO. So this one. That's why we want to compute the WHO, this one. So it will be delta was sum divided by the hidden layer results. So this is the case. So here the hidden layer results. So that means delta WHO, that means the rate of change of W, the W values, it will be the delta output sum divided by hidden layer results. Okay, hidden layer results. So delta output sum divided by hidden layer results. We can see delta output sum is what? We have already computed this. This is our the case. 0 minus of 0.13 something. Alaikum salam. Hello. Okay, so we can see the delta weights. We can see this is so that means the delta was sum divided by the hidden layer results. These are the hidden layer results. Then we will get what? We will get these values. Okay, these values. So these are our delta weights. The delta weights means, that means we need to update the weights using these values. Using these values. So we can see here there is the delta weights. So the previous weight 0.3, 0.5, and 9. Then the new weights will be the previous weights plus of delta weights. Okay, so then we will get this. So these are the values of our new values of our weights. So these weights. Okay. Uh, so I think we have already, it is 12:40. Uh, uh, so we will continue our discussion, that is how to update these weights in our next class using the backward propagation. Thanks everyone for joining this session. See you in your next class.
Sir, when we will get our midterm marks?
Maybe this week.
Okay, thank you, sir.
Okay, in this week, inshallah. Okay, thank you.